An experimental setup of phase separators used in a school laboratory is shown in the figure 1. As shown, XW, X1 represent the heights to the mark M of the relevant indicator from the water and liquid surfaces. In the beakers respectively. Part A1. What is the purpose of using a clip in hair separator? To maintain liquid levels in tube. You can write to maintain liquid levels. In part 2, the densities of water and liquid are dW and dL respectively. If HW and HL represent the heights of the water column and liquid column in glass tube as measured from the mark M of the respective indicators. Derive an expression for HL in terms of HW, DW, XW, DL and XL. I will draw the diagram. In the given figure, there are two beakers. Height from water level to mark M is given as XW, water. Height from liquid level to mark mark M is given as XL. This is the mark M. And corresponding water height from mark M is HW, corresponding liquid height is HL. We are using this strip to maintain liquid levels. Now we have to write an expression for HL. In writing an expression for HL, we have to use Pascal principle. According to Pascal principle, we know that there is the same pressure in this point and this point, because of pressure of this point equals to pressure of this point, same liquid and same height. And pressure at this point equals to this point, pressure of this point, same liquid and same height. But we know that pressure of this point equals to pressure of this point because of both points are in atmospheric pressure. This point is open to the atmosphere and this point also open to the atmosphere. Then we can equal pressure at this point A and pressure at point B. I have considered this point as A and this point as B. Then we can write pressure at A equals to pressure at B because of pressure at A and B also, A and B points is equal to the atmospheric pressure. This point of this pressure of this point equals to pressure of this point, and it is equal to the atmospheric pressure. Pressure of this point equals to this point, and it is also equals to the atmospheric pressure. Then we can write an expression for pressure at A. We can consider pressure inside pressure of this tube P naught. Then we can write P naught plus HW plus HL. HW plus XW. It is the total height of this water column. HW plus XW. Total height, it is the H value, dWg. H rho g. We have to use hydrostatic pressure. Then this expression is representing pressure at point A. It should be equal to pressure at point B. Then pressure at point B, P naught plus HL plus XL dLg. Now we can cancel out P naught and P naught. Then we can cancel out G and G. Now we have subject HL. We have to write an expression for HL. I will expand the bracket. HW dW plus XW dW equals HL dL plus XL dL. Now we have subject HL. Therefore, I will bring this term to the left hand side. HW dW plus XW dW minus XL dL equals to HL dL. Then we can divide all terms by dA to remove dA term from right hand side. Divide by dA. Then we can cancel out dA term. We can get an expression HL equals HW dW divided by dL plus XW dW divided by dL minus, we can cancel out dA term, then XL. It is the expression for part 2. Then part 3, if the expected heights of liquid column and water column are significantly different to each other, more attention has to be paid on one height than other when planning out the experiment to take a set of range and photographs. What is the height you pay more attention? One with a smaller height or larger height. Explain your answer and give reasons. We have to consider larger height because of it will reach the maximum height of tube first. When getting a range of values, when getting a set of values, we have to consider large height. The maximum value of large height should be less than the maximum height we could maintain in the tube. Then we can write answer for part 3, large height, and we have to write the reason. Reason is it will become to the maximum height of tube first. In part 4, every time after changing the heights of liquid and water column in tubes and crossing the clip, you need to make another adjustment before taking measurements with regards to new heights. Write down experimental procedures which you should follow to make this adjustment. We have to make an adjustment such that indicators have to be readjusted until they touches the surface of the water and liquid levels in beakers. Then we can write answer for part 4. Indicators have to be adjusted such that indicators touch the liquid surfaces. Touch liquid surfaces. Liquid surfaces means water surface and liquid surface in beakers. Then part B, the apparatus shown in the figure 2 can be used to vary the air pressure inside the tube of the hair separator. This system works on Bernoulli's principle. The air pressure inside the tubes of hair separators. The air pressure inside the tube T can be changed by adjusting the speed of the narrow water jet passing through the section X of apparatus with the help of the tap. The position A of the apparatus shown in figure 2 can be connected to be position A of the tube as shown in the figure 1 to make an improved version of hair separator. Part 1. Write down the procedure. Write down the procedures used in hair separators available in school laboratory and improved version of hair separators mentioned in part B when establishing the liquid column of tube. We can write when using hair separators. We can maintain corresponding liquid columns by sucking air from in tube with mouth. We can write sucking with mouth. We have to open this strip and we have to suck air inside the tube to maintain corresponding liquid height. Now for the improved version of hair separators, it means the apparatus shown in figure 2, we can maintain corresponding liquid column by changing speed of water flow by controlling the tap. We can write for the improved version by controlling speed of water flow using the tap. Part 2. If one main advantage using the improved setup mentioned in B over the apparatus generally available in the school laboratory, we have to write one main advantage. When using this setup, we can write sucking is not necessary. It is the main advantage. Then part C, the graph plotted using a set of readings obtained from the improved apparatus mentioned in B above is shown below. The graph shows the variation of heights HW and HL of the liquid columns of water and sulfuric acid respectively. In this experiment, you are provided with a scale which can measure length with an accuracy of 1 millimeter. What is the maximum fractional error associated with the HW measurement taken in the experiment? Maximum fractional error. We can find the minimum height of water column used to plot the graph by using the graph. Minimum height of water column is, we can observe maximum fractional error for the minimum height. What is the maximum fractional error associated with HW measurements taken in this experiment? Minimum water height is 100 millimeters. X-axis is given with HW into 10 to the power minus 3. It means 100. It is in millimeters, and first point plotted in the graph is 100 in the x-axis. HW value is 100. Therefore, maximum fractional error 1 over 100. 1 is the minimum least count. We can write the equation. Fractional error equals to least count divided by reading. Least count is 1 millimeter. We have to divide by 100 because of 100 millimeters is the minimum reading obtained to plot the graph. You can use values in x-axis and first point to find this reading. Then part 2, using the 2 points P and Q on the graph, calculate the relative density of sulfuric acid. We have to consider P and Q points to find the gradient. I will rearrange this equation to find the relative density of sulfuric acid. Then HW for the x-axis and HL for the y-axis. We have subject HL value. HL equals x-axis HW, then dW over dL into HW plus XW dW divided by dL minus XL. It is in the form y equals mx plus c. Now we can equal gradient to this value. This value means dW divided by dL. dW divided by dL means reciprocal of relative density of sulfuric acid. We have to find dL over dW, but in this equation, this term is reciprocal of specific gravity or relative density of sulfuric acid. Then we can get 1 over gradient. 1 over gradient equals to dL over dW. This is the relative density of sulfuric acid. Then getting 1 over gradient, we know that when getting gradient, we have to get the ratio between difference of y values and difference of x values. But when getting 1 over gradient, we can write difference of x value divided by difference of y value. Difference of x value for given 2 points, 480 minus 130 divided by 270 minus 80. It should be equal to relative density. We are normally using S for the relative density because of relative density is specific gravity. Then we can subtract 0 minus 0, 0, 8 minus 3, 5, 4 minus 1, 3, 0 minus 0, 0, 7 minus 8, 17 minus 8, 9, Now we can get 35/19. It is approximately 1.84 specific gravity or relative density of the sulfuric acid.